Here is the unit 2 continuation part. Let me see one by one. So design Chebyshev filter. So the given data are here. That is, first we have to write the passband attenuation, passband frequency, and stopband attenuation, stopband frequency. First step, we have to find out the passband and stopband attenuation in the decibel format. So for that we have to use the formulas alpha p, that is equal to minus 20 log alpha p, that is 20. Next, to stopband attenuation, we have to use alpha s. So choose the t and determine the analog frequencies. So ohm p and ohm s. So that is ohm p is equal to omega p by t, ohm s is omega s by t. So to step 3 is to find the order of the filter, that is n is greater than or equal to cos h inverse, that is root of 10 to the power of 0.1 alpha s minus 1 by 10 to the power of 0.1 alpha p minus 1 divided by cos h inverse ohm s by ohm p. So when you are substituting the value, we will get the answer as 1.45. So rounding this value to the nearest integer value, so that is n is equal to 2. So step 4, we have to find out the poles of a Chebyshev filter. So for finding the poles of the Chebyshev filter, we can determine this in the formula of Sk is equal to a cos 5k plus jb sin 5k. So k is equal to 0, 1, 2, etc. up to n. So where phi is equal to 2k plus 1, n minus 1 into pi divided by 2n. So calculate the a value, b value, epsilon value and mu value. So for finding the epsilon value, we have to use the root of 10 to the power of 0.1 alpha p minus 1. So substituting the values, we will get a epsilon value. Next, mu value. So epsilon inverse plus root of 1 plus epsilon power minus 2. So we will get the mu value. A means there is ohm p into mu power 1 by n minus mu power minus 1 by n by 2. So we will get A value. B is equal to ohm p into mu power 1 by n plus mu power minus 1 by n by 2. So then we will get the B value. So substituting all the values, we will get phi substituting the k equal to 1 and 2. So then we will get Sk is equal to a cos 5k plus j b sin 5k, that is k equal to 1, 2. So when substituting 1, S1 value will be get, and when substituting 2, k equal to 2, we will get a S2 value. So next step 5 is to find the denominator polynomial of the transfer function using the above poles. So when we are multiplying, we will get the round of poles, that is s square plus 0.51 is plus 0.33. So next step 6 is to find the numerator of the transfer function, which will be depends on the value of n. So here we have to note one value, one point, that is if n is even means we have to substitute s equal to 0 in the denominator, and the result will be root of 1 plus epsilon squared. Find the value. So the step 7 is the transfer function. We have to find out. So there is a h of s is equal to numerator by denominator. So step 8 is using the fractional partial fraction expansion. So that is h of s is equal to summation k equal to 1 to into a s by s minus pk, that is equal to a1 by s minus p1 plus a2 by s minus p2. So substituting the values, we the private answer. So next step 9. Now transform the analog poles pk into the digital poles. So that is e to the power of pkt to obtain the digital filter. So first we have to substitute, that is the value is summation k equal to 1 to n ak by 1 minus e to the power of pkt z inverse. So we get the answer, that is h of z. Next thing will be the converting the, we have to find out the filter design using the frequency translation, that is high pass filter, band pass filter and the BRF, band rejection filter. So the digital filter can be converted into the digital high pass, band stop or another digital filter. So these transformations are given below. So low pass to low pass, S Z inverse, that is Z inverse minus alpha by 1 minus alpha Z inverse. So low pass to high pass means that is Z inverse tends to Z inverse plus alpha by 1 plus alpha Z inverse. So where alpha is sine omega p minus omega dash p by 2 and sine omega p plus omega p dash by 2. So here we have alpha is equal to cos omega p dash plus omega p by 2 by minus cos of omega p dash minus omega p by 2. So for low pass and new low pass filter we will use this figure. Next, for low pass filter we have the Z inverse, we have to substitute this formula and find out the values. For this low pass filter they have to find out this value. So there is Z inverse value is given, so we have to find out the value. Here we have to use the alpha is equal to cos of omega p minus plus omega is by 2 divided by omega p minus omega p by 2. So that is we have to use the upper cutoff frequency as well as the lower cutoff frequency. So k is equal to cot of omega u minus omega l by 2 tan of omega p by 2. So likewise here we have to use that k is equal to tan of omega u minus omega l by 2 tan of omega p by 2. So next we are going to see about the analog domains. So the frequency transformations can be used to design the low pass filter with different passband frequencies. So there is a S tends to S by ohm C and here S tends to ohm C by S for low pass to high pass. For low pass to band pass means S tends to S square plus ohm 1 ohm L ohm U by S into ohm U minus ohm L. Low pass to band stop means S tends to S into ohm U minus ohm L divided by S square plus ohm L ohm U. So here we have to ohm R is equal to minimum of AP B mod B is given, and that is A value is minus ohm L square plus ohm L ohm U by ohm L into ohm U minus ohm L. Here ohm L into ohm U minus ohm L divided by minus ohm L squared plus ohm L ohm U. So B we have to find out ohm 2 squared minus ohm L ohm U by ohm 2 into ohm U minus ohm L. So here ohm 2 into ohm U minus ohm L divided by minus ohm 2 squared plus ohm L ohm U. Okay, likewise we have to find out the answer. So here the Chebyshev filter we have to use the feed. So that is they have given the answer. The next thing will be design the Chebyshev filter, low pass filter with the specifications. Alpha p is equal to 1 decibel ripple in the passband. So here we have seen that n is equal to 2 and h of s is 0.212 by s square plus 0.4172 s plus 0.3. So next is the enumerate the various steps involved in the design of low pass filters, digital Butterworth IAR filter. So here we have to design the Butterworth digital filter using the impulse invariant transformation. So here we have used the n is equal to 4 and then apply the equations and then find out the values. The next question they have chosen that design a Chebyshev low pass filter by using the bilinear transformation as well as the impulse invariance transformation. So within these two methods we have to find out the answers. By finding the we already know that n value. By substituting the n values we will get the answers. Next, use the backward difference for the derivative to convert the analog low pass filter with the system function. So here the h of s is given, that is 1 by s plus 2. So for that we have to find out the h of z as a value. Likewise for analog transfer function we have to determine the h of z using the impulse invariant techniques. So here is one question, that is prove that ohm c is equal to ohm p by 10 to the power of 0.1 alpha s minus 1 the whole power 1 by 2 n. that is ohm s by 10 to the power of 0.1 alpha s minus 1 the whole power 1 by 2n. So there is a modulus of h of e to the power of j ohm the whole squared is equal to 1 by 1 plus ohm by ohm c the whole power 2n. So we know that modulus of h of j omega the whole squared is equal to 1 by 1 plus epsilon squared into ohm by ohm p the whole power 2n. So when substituting the values we will get that is c into 10 to the power of 0.1 alpha is minus 1 the whole power 1 by 2n. So we'll get 10 to the power of 0.1 alpha is minus 1 by 10 to the power of 0.1 alpha is minus 1 the whole power 1 by 2n. So we'll get the ohm c value. So that is ohm s is equal to ohm p into 10 to the power of 0.1 alpha c alpha s minus 1 by 10 to the power of 0.1 alpha s minus 1 the whole power 1 by 2n.